Hello everyone. Today I'm excited to present a new paradigm of serverless computing that speeds up the difficult and important problem of motion planning for robotics. Let's start off with some background on cloud and fog computing. In the last decade, we've seen cloud computing explode with providers like Amazon Web Services, Microsoft Azure, and Google Cloud. Cloud computing allows for easy scalability and easy management of resources, as you no longer have to manage the infrastructure on which your compute runs. This also enables new models of computation in different domains, and we shall leverage one of those new models of computation in robotics today. Fog robotics extends the cloud to also leverage tools at the edge, which means servers closer to the robot or on the robot itself, and dynamically allocates resources between the two to get optimal performance. Functions as a Service, or FaaS, is one such new paradigm of computing that allows developers to define functions that take in arbitrary input and produce arbitrary output on these cloud infrastructure providers. These functions are executed on demand, and users are only charged for the amount of time that they actually run compute. Although each individual function is not that powerful, the scalability of the cloud allows us to execute many such functions in parallel and gain potential speedups in many different applications. These functions do come with limitations, however. Firstly, there is no easy way to store or share state between various executions of a function. Secondly, it's difficult to communicate between functions, as lambdas do not allow for inbound network connections on Amazon Web Services. Next, we posit that motion planning is an intermittent workload. Take, for example, a robot that's tasked with cleaning a home or an office. There are two kinds of motion planning problems that it needs to solve. The first is a 2D navigation problem to get from point A to point B in the room. This problem has relatively low computational requirements and can be easily solved on the onboard computer of the robot. Once it gets to a desk, though, it has to solve an 8-dimensional manipulation problem to actually pick and place different objects. This problem is exponentially harder than the 2D manipulation problem and is much slower to compute on the robot's onboard computing system. There are two main characteristics we want from such a motion plan. First, we want access to reusable motion plans to avoid recomputing for every object that we have to pick and place on this disk. Second, we want that initial motion plan to be very quick to avoid the robot spending a lot of idle time waiting around at the desk, not doing anything. To provide access to reusable motion plans, we decided to use graph-based motion planning, in particular, the tried and tested approach of probabilistic roadmaps, or PRM. PRM generates a connectivity graph of the space that can then be used as a data structure to query against to generate motions. There has been a lot of subsequent work on PRM to parallelize it, as well as extend the method and improve it for other use cases. However, we are not aware of any method that uses this new paradigm of serverless computing to parallelize PRM. Next, let's talk about how we actually speed up these graph-based motion planning methods. One simple way is to provision a high-end computer on the cloud, as we saw before. This lets us offload the high-dimensional planning task to this computer. However, there are two main disadvantages with this approach. First, there is low utilization of this high-end computer due to the intermittent nature of motion planning. Second, this computer has poor scaling with many robots, as if all the robots request a motion plan at the same time, it will get backlogged and not be able to respond to them quickly enough. This leads us to the question, can we speed up graph-based motion planning without provisioning an always-on high-end computer? We theorize that functions as a service is a good fit for intermittent motion planning. The reason for this is we're able to spin up these functions on demand, and we're only paying for the amount of time that we have these functions running, and not for the lot of idle time that the robot is spending on 2D navigation tasks. Thus, we now frame our proposal as the following. We want to speed up intermittent graph-based motion planning by efficiently parallelizing it over hundreds of serverless functions. There has been a lot of prior work on cloud robotics and motion planning. Last year, there was a paper that explored tree-based motion planning using these same Lambda serverless functions. However, tree-based motion planning doesn't lend itself to multiple queries as easily, and parallelizing graph-based methods requires a different approach than was taken for tree-based methods. Additionally, there has been a lot of past work that demonstrates the need of efficient allocation of resources to perform motion planning, but none of them use these serverless computing units that we're using in today's paper. Given this motivation, let us provide some more formal context for the problem. Let's start with a brief description of the KPRM star algorithm that we will parallelize today. There are two main steps in KPRM. First is sample points and connect points to k nearest neighbors. We can see this in action on the diagram on the left. As the graph grows, more edges are added and the entire graph becomes more dense. Given a start and a goal, we can now use the edges of this graph to go between those 2 points. PRM gives us two main guarantees. One is probabilistic completeness, which means that if there is a solution, we will find one given enough time. Kahneman and Frizzoli also showed that choosing a particular value of k, as shown in the slide, also gives us asymptotic optimality, which means that given enough time, our solution will converge to the optimal solution. We made a few observations to motivate our current method. As mentioned before, sharing data structures between individual executions of lambdas is slow. Thus, we quickly ruled out methods that involved sharing nearest neighbor structures across all these lambdas. The second observation we made is that the connectivity step of PRM is orders of magnitude slower than the sampling step. This means that we can perform a lot of repeated sampling work without too much extra cost. The final observation we made is that random number generation that is used in PRM samplers often generates the same sequence of points given a seed. Thus, our proposal was to use a shared random seed across all lambdas to duplicate low-cost sampling work. This means that all lambdas will sample the same set of points given the same seed. However, we avoid sharing data structures between lambdas, which is a much slower process due to network latency. Let's explain this visually. On the top, we have 3 instances of our lambda running. And as before, the point in red is the point that's being actively connected. We will see this point move from lambda to lambda. On the bottom, we have the cumulative graph as present on the robot. As we're sampling points, we see that different lambdas are attempting to connect each vertex. And as we go further into the algorithm, we see that each lambda only connects a subset of the edges. Finally, we have this cumulative graph at the bottom, which is identical to the graph produced by our serial KPRM method. This means that our method also inherits the asymptotic optimality and probabilistic completeness of the serial method. We see that the 3 lambdas on top are only connecting approximately a third of the edges, which allows for efficient parallelization. Our ideal experimental setup would involve the robot directly talking to the lambdas and receiving responses depending on how much compute it needs. However, due to the limitations mentioned earlier, we need lambdas to communicate with each other for some work-sharing methods. Therefore, we provisioned a lightweight and cheap 2-core coordinating server with a public IP. Lambdas can then connect to this public IP to communicate with each other. All our experiments generate a graph of 17,000 vertices and approximately 700,000 edges. All our experiments are run over different random seeds and varying number of lambdas. We start off with our favorite benchmark, the Open Motion Planning Library's twisty-cool experiment. On the x-axis, we have the end time of the entire algorithm in milliseconds. On the y-axis, we have the cost of the entire algorithm in dollars. Note that these do not start at 0 for easier visualization. This trade-off between cost and the end time of the algorithm is what we are really interested in as practitioners. We want to be able to reduce the amount of time the robot spends planning motions without paying too much extra money. We look at our first work-sharing method where we equally distribute vertices among lambdas, and we see that we do get a nice trade-off where we're able to pay 1/10 of a cent more in order to get results almost 4 times as quickly. We have other synchronous work-sharing methods where we distribute the work package to lambdas in different manners. We see that this method is more expensive than the method without work-sharing, but does give us quicker end times. Finally, we tried out an asynchronous work-sharing method, which gives us the best of both worlds. We have lower costs and better end times. The main takeaway from this graph is that we now have a lot of power as practitioners. We can now choose an amount of money we're willing to spend, choose how much we value robot idle time, and also choose how quickly we want our motion plans to compute. This graph will then spit out a specific set of parameters we can use to generate that kind of motion plan on average. This means we no longer have to wait around forever for our robots to compute motion plans, and instead they can spend more time doing useful work. Finally, for comparison, we put a local baseline here, but it actually didn't even fit on the graph because it took over 80 seconds to compute on a local 8-core machine. The next set of graphs we show have more to do with parallel efficiency. On the x-axis, we have the number of lambdas from 16 to 128. We also have two local baselines of 4 and 8 cores. On the y-axis of the first graph, we have the time to complete the algorithm on a logarithmic scale. We see that we get pretty good scaling up to 128 lambdas with this method. On the second graph, we have the fraction of time spent on three different things. One is startup overhead, the second is the time to sample different points, and the last is the time to connect points. Note that by the time we get to 128 lambdas, the startup overhead is a major part of the whole algorithm. We could not scale beyond 128 lambdas directly using this method because of the limitation of the startup overhead being so large. Instead, we controlled for startup overhead and ran additional experiments up to 512 lambdas. When we did this, we observed better scaling. However, we do note that the parallel efficiency starts to drop as we get to around 512 lambdas. This is because the sampling time is now a much greater fraction of the overall time. We ran the same set of experiments with the SE3 cubicle scenario with similar results, and we also see pretty good scaling for this method. We ran some more experiments on a fetch desk decluttering scenario. Over here, we see that the parallel efficiency is much worse than the previous two cases. This is because the sampling time is a much more significant portion of the overall compute time than the SE3 cases. Here is another fetch scenario where it's decluttering a bookshelf, where we see similar results. And here are the results for parallel efficiency for this scenario. The main takeaway from these set of graphs is that you now have the power to decide exactly how long your robot will take to plan motions, and you only pay a marginal increase in cost for this quicker compute time. We did run into a few problems, however. Firstly, as mentioned before, we want to scale beyond 128 lambdas once we have serverless providers who can provide lower startup delays. The second issue with this algorithm is that in dynamic environments where the objects are moving a lot, we might have to stream a lot of point clouds to AWS lambdas, which can result in much slower performance. Finally, we would like to work on theoretical guarantees on a distribution of possible end times given a distribution of start times of the lambdas. Thank you so much for listening, and I would welcome any questions or feedback either now or over email.